Sorry, dealing with some technical issues here. For those of you who commute, if you didn't hear, there is a presidential candidate on campus to this afternoon at 2 p.m. out at the Mullet Arena, the kind of tiny arena, and kind of closer to the lake. So if you're normally commute around the afternoon time, then it might be good to try to leave earlier or wait a lot later because it could gunk things up a bit, especially kind of going north towards Scottsdale. All right, so the schedule kind of moving forward here. So lab 8, we've got this data collection lab that you've been doing this week. So this is the type of data that you'll collect for your input modeling report, and this is giving you some practice at to doing that type of input modeling. And then next week is provided for you and your groups to spend the time you would be spending on lab to go out and try to take some of that input modeling data. For some of you, if depending on your system, you might already have that data available to you. So if there's someone on your team that already has access to data at a company, for example, that you're thinking about modeling some process of, then you may not actually have to go out and take the data. But in that case, you may just need to sort of look at the data and then be able to sort of pick aspects out of it that, again, demonstrate to me that you know how to take the data and then generate an input model that you can use in your eventual simulation diagram that you're going to draw up in Arena. Then labs 9 and 10 after that are regular weekly schedules. So that's just the kind of advanced topics in Arena that will hopefully help you to do things like batching and so on that are usually useful in modeling these more sophisticated things. And then after that, there's no extra labs. So the extra weeks there, that lab time is meant to be available for you to work on your final project and to get assistance from say the TA for that. So final project. I've gone over this. The big thing is this Friday. So, just coming up right here this week. That's your names of your team members there. Thanks to everybody who submitted that so far. And as I get those in, I've been trying to form those groups. There is a Google Drive spreadsheet that is linked from a recent announcement, as well as in the final project module, where some students have put their names where they're looking for groups. So if you put your name down there, go back to it, look for anybody else who's put their names there, and then reach out. Hopefully most of that will be done Friday. I've extended the availability a little bit longer, which gives me time to wrangle things. So if I notice that there's students that are still having trouble finding, then I can do some matchmaking. But it's always better for these groups to be formed among people who, sort of agree to be put together rather than me just randomly choosing people to put together. And then roughly a week later or so, I think a little bit longer than that, than the input modeling report is due, and that's basically next week's lab report. So in lieu of a lab report, then it's the input modeling report, which is a short report which gives me in roughly a couple of sentences to a paragraph a description of your system and the problem that you're sort of attempting to model, or the problem that you've noted that there needs to be some work studying, and then a list of the variables that you'll need to gather, both the input variables and the output measures. And then a demonstration for at least one or two of those input variables that you have the data and you can do an input model. So showing us you kind of done the process that you practiced in lab 8. So we're looking for in the input modeling report. So there's a little more details there on the assignment that is there posted on Canvas. Otherwise, ICA is available. Homework H it will be made available shortly. It's technically released after lecture H, which is coming up next week. So that will be a practice in input modeling for question 1 and a practice of output validation for question 2. And then only one homework after that. So that's homework J2, which is sort of a synthesis homework where you'll kind of combine a couple of things we've been talking about in lecture with Arena stuff you've been doing in lab. We use it as an ABET metric. We capture some ABET metrics with it. And so it's a special assignment that whereas all the other homeworks, the lowest one will be dropped. This one, even if this is your lowest, it won't be dropped. So the lowest one will come from the other homeworks. This homework cannot be dropped. So everybody should make an attempt at this homework J2. And likewise, there won't be a solution set that's released for homework J2 because we capture metrics and we try to have to maintain some consistency from semesters to semester. So it adds some extra constraints on what we can release and so on and so forth. So look out for that. So any questions? Everybody knows the big pressure is to get your groups finalized so that next week, as kind of a lab exercise, you can get that input modeling report done. Okay. All right, so we've been talking about if you have a diagram like this, that's fine. That's the basic structure of how things move through your system. But the hidden thing that's there are the input models. And so this whole unit is about getting the input models right. So this is like a queuing node, like you might put together in queuing networks, like you do in like 470. And as you learn about queuing nodes, there's ways in which you specify, like the big difference between one queuing node and another isn't the structure of the node, it's how things arrive to the node and how quickly they are dispatched through the node. And so based on that, then like there is this Kendall's notation that again you'll learn in 470, and it's these shorthands. So an MM1 queue, that means you've got one server. So one server here, capacity of one here, and the service time M is short for Markovian memory list. So that means that the service time here in the middle one, that is going to be an exponential distribution. And then this first M, also short Markovian memory list, means that the interarrival times will also be exponential. So there are a bunch of different ways that you can have the exact same queuing node, the same structure, but you just change the input model. So an MD1Q, so I'm not going to test you over Kendall's notation in this class, but it is something that you should hopefully see in classes that talk about queuing networks like 470. And then so these letters are going to change, and they're going to totally change that stats that come out of this queuing node. So if it's an MD1 queue, the arrival process still has exponential interarrival times, but the service process is deterministic. So that would mean that even though they arrive randomly, they're always served exactly 2 minutes. There's no variation whatsoever. And then there's different ways you could also flip that. You could say they arrive every 2 minutes on the dot, no difference there, but they have exponential service times, kind of flipping that, and so on and so forth. And so you can get major elaborations here. So this is a memory M to the X is a memoryless interarrival times, exponential interarrival times of batches that are distributed according to X. So there's this other random variable there. And then E sub K, well, that's that Erlang K service time. So that's a way of saying that there is effectively the service here is the sum of K exponential random variables. So that's so that's how so you capture a lot in this shorthand notation. And if you were to look up the Wikipedia page on Kendall's notation, then you'd find out all the different ways that you could write out this, all for just a single queuing node. So that just goes to show how important it is to get the input models right. Otherwise, we wouldn't have these complex notations, which for the exact same diagram, you get totally different notations for totally different system phenomena. So one of the things you do in queuing networks is you basically string together a bunch of nodes that look exactly like this. So the output of one node is the input of another. And then you specify, well, this node has this input distribution for interarrival times, and this service distribution, and this node is got a different service distribution, this node's got a different service, and so on and so forth. And so you string all those things together and you look at what the system does. But the only thing that differs between the nodes is effectively the input model. So we really got to get that input modeling right. So that's what we've been studying here in this unit, is how to pick those input models based on data that you've gathered from the real world system. So how to choose those. And so this unit's we talked about collecting the data last time, and then we missed a couple of slides on probability plots that I'm going to go over here in just a slide, but basically how to find the right family. And then for the rest of this lecture, after we cover those slides that we missed, then it's and that should be a G3. Again, I didn't fix all of these there, but then we'll talk about once you've figured out, okay, it is definitely in the normal distribution, the normal family, which are the right parameters for that normal distribution. And then after I've picked my parameters, how do I evaluate how good, it's maybe the best fitting distribution, but how good is the best fitting distribution? So that's what we'll talk about here. So where we left last time is we talked about these probability plots. And so a probability plot is either a PP plot or a QQ plot. Q is short for quantile, P is short for probability. These are the so-called fat pencil tests that sometimes you'll see in some other classes as well. And so the basic idea is that you're in both of them going to sort your data, and then you're going to plot the sorted data in different ways relative to your hypothetical family that you're fitting to them. So a QQ plot compares the quantile functions, the inverse CDFs. And so in that case, you plot your data, your sorted data against and I'm going to drill into each one of these in a second here, but this is just a summary here, is that you plot the sorted data, the raw data itself, against the rank of that data, where it is in the sorting order, typed through the quantile function for your hypothetical distribution that you're evaluating whether it's a good fit or not. So if you're evaluating whether a normal distribution is a good fit for these data, then this would be the inverse or an approximation of the inverse CDF for a normal. And then what do you plug into that? Well, if it's an inverse CDF, it takes an argument from 0 to 1. So you plot the normalized rank. So you say, well, if this data point is 45th in the rank, I'm going to do 45 minus a half just to kind of get it centered a little bit, divided by the total number of data. And then that will give me a number between 0 and 1. I plug that into the quantile function, and then that will give me, if it was this distribution, this will say this is the outcome that matches that quantile. And then they're kind of comparing them and seeing if they line up. The PP plot is sort of a very similar idea, but it does it by plotting the ranks instead of plotting the values. And so here, instead of plotting the raw data on the x-axis, I plot the rank of the raw data after it's been sorted. And then I plot it against the cumulative distribution evaluated at that data point. So the cumulative distribution will give me a number between 0 and 1. This will give me a number between 0 and 1. Both of these are probabilities. That's why it's called a PP plot, because you're plotting probability against probability. Here you're plotting quantile versus quantile. So we have these two because they kind of have different strengths. We always do the QQ plot first because it's kind of the coarse-grained fit. A PP plot isn't very conclusive if the QQ plot doesn't match things up first. So if you have a bad matching QQ plot, then you're not going to have a very conclusive PP plot. So that's why you typically do the QQ first and then the PP. And again, I'm going to drill down and give examples of both of these just here in a second. But so the idea here is the QQ plot amplifies the differences between the tails of the distribution. So not the big hump in the middle, the stuff that's happening out on the edges. And once you get those right, then the PP plot helps us to refine the the distribution. So for all distributions that sort of are very similar in the tails, then the PP plot helps amplify differences in the main bulk of the distribution so that I can say, well, of the ones that match in the tails, which one is the better fit? So let's see example of that. So this is the QQ plot. Again, the idea here, sort all the data, plot the points directly against whatever their rank is, pipe that through the inverse CDF for my hypothetical distribution, otherwise known as the quantile function. So this will give me the quantile. So what do I mean by the quantile? Like if I were to say, like, what's the 95th percentile score on the midterm, then you just give me a score. That's kind of a bad one because scores are also, but what if I said, what if it's the 95th percentile height in this classroom? Well, if we ranked all of your heights, we could say, what is the height that is taller than 95% of everyone else in the classroom? That's what we mean by quantile. So that's what we're plotting here. We're saying for this data point that's been sorted. So this data point is effectively, if let's say this data point is the 65th percentile, the 0.65 quantile, then what this extract is saying, if this was a normal distribution or a Weibull distribution or whatever, we're saying for that hypothetical distribution that we're evaluating, what is its 65th percentile, 0.65 quantile, and then that's going to spit out. So this might be a height of 5'2", and this would spit out a height of 6 foot. And we're like, oh well, those potentially could be way off, but the quantile, it's really not about the absolute match, it's whether they fall on a line, and that's what we're going to see here. So this was the data I showed you last time. I just generated data, synthetic data, that from a normal distribution with a mean of 5 and a variance of 9, so a standard deviation of 3. And I took all those data and then I sorted them. So these are the values that come out of that I'm plotting here. And then each one of these points, I then took, I said, let's pretend I don't know where those came from. So I generated the data, but then I just forgot that I generated the data. I got the data from some other source. And I look at that data and I think these data might be normally distributed. I don't know what mean, I don't know what standard deviation. Right now, I'm just trying to see, do they look like they're properly bell-shaped? Do they have the right shape of a normal distribution? So what I do is I take a standard normal and I say, I know the inverse CDF for a standard normal. So I'm going to take each one of these, so this formula here, I'm going to take each one of these data points, figure out what its rank is in the sorted order, take that rank, plot it in to the inverse CDF for my standard normal, and then see what number comes out. And so what I get out of that then is this line in here. So these points fall pretty much on this line. So notice that the x-axis has a very different range than the y-axis. And that, but that's fine. That's not what we care about for a QQ plot. We care about, does it fall on this line? And that tells me that, hey, a normal distribution looks pretty good here, at least in the tails, that this is a candidate distribution for these data. I should keep normal in my candidates. Now, if I instead took data that was generated from an exponential and did the same thing, I'm saying I look at this exponential data and for whatever reason I want to evaluate it against a normal, then I get a QQ plot that looks like this. So the same process, but I use a different inverse CDF, a different quantile function. I use the inverse CDF for, I'm sorry, I got that backwards. It's the same inverse CDF because I'm showing the hypothetical normal, but different data. So I used, so I sorted the data the same way, but it just has a different distribution. So it has its own different quantile. So when I plug them into the hypothetical quantile function, then I get this this ugly thing that bends. And so this is like the best fitting line that I can find, and it's nowhere near that line. So that tells me this is a poor fit. That's one thing that says I should probably say that for these data, I shouldn't use a normal. But then the question is, what should I use? And so I'm not going to ask you to memorize this next table, but you should know that for a quantile function, there's this regularity that based on the patterns you see, it can guide you toward a better distribution. So if I look at these, I could say that like, well, if all but a few points fall on a line, that's maybe okay. That just means there's some outliers in the data, and maybe I'm okay with that if there's only a few of them. But if there's these more systemic or systematic differences, so like down here, a curved pattern with slope increasing from left to right, or a curved pattern with slope decreasing from left to right. Well, if I look back at this is a curved pattern, and the slope is steep here, and it gets shallower over here. Well, that, is a curved pattern with slope decreasing from left to right. This tells me that the data are relatively skewed to the right. Now, given that I know that I generated data from an exponential, that makes sense to me because an exponential has data skewed way to the right. So that's kind of what I expected. But if I didn't know they were from an exponential to begin with, then that would tell me that there are more extreme values on the right than my hypothetical. So I chose a normal distribution. What this curved pattern with slope decreasing from left to right tells me I should have chose something that has right skew relative. So, or whatever I chose, I needed to choose something with more right skew than the thing that I chose. I happen to choose a symmetric distribution, a bell curve. And what this pattern tells me down here is I should have chose something that was stretched out on the right more than the one that I actually chose. So that helps guide me towards a family of distributions that is more appropriate for these data. So that's that's why we've got a bunch of these patterns here that if it matches one of these patterns, it can help guide you to other distributions. So I choose one that's more symmetric, less symmetric, skewed one way, skewed another way, and so on and so forth. And then, other things that are kind of related to that staircase pattern, plateaus and gaps. Well, that suggests that I'm trying to fit a continuous distribution to potentially discrete data. So, that's one of those cases. If you see stair steps or plateaus and gaps, maybe go back and look at the raw data and sort it and see, do you see a bunch of repeated values? If you see a bunch of repeated values, maybe it's actually a discrete distribution. And what you should do is just see what is the frequency of those repeated values and just use an empirical distribution for if there's only a handful of those values, only 3 values in the output, but they occur repeated times, then maybe you just come up with those 3 probabilities. All right, so questions about this QQ plot thing. That makes sense, how to interpret or what's going on here and potentially how to interpret it. Okay. All right. So a lot of times when if you're doing an input model, like in your input modeling report, you're trying to justify that you've chosen a model that is a good fit to your data. Some of the things we like to do is just include a QQ plot. It doesn't have to be in your main, sometimes it's in the appendix, but then we'll refer to it and say, we validated the model using a QQ plot and a PP plot, see figure A1 and A2 or something in the appendix. And so if I include this, it's a compelling argument that based on the QQ plot, I've chosen a good family for these data. But it's not totally conclusive, and that's why we also have the PP plot. So ideally we'd like to check both. So once the QQ plot looks good, then you flip and do the PP plot. It's a very similar idea, like I said before, sort the data, but now you're just changing what you're plotting. So now you plot the rank against the CDF of the hypothetical distribution, evaluated at the point corresponding to that rank. So if I do that, so here, this is my example where I generated data from a so-called gamma distribution. So a gamma distribution is actually basically an Erlang K distribution, but it allows you to make the K a non-integer value. But so this gamma distribution, these are the 2 parameters that I chose here, and that is this red line. And then this is the histogram of the actual data that I generated. But notice that a normal distribution with a mean of 50 and a variance of 15.8 is pretty close to this histogram as well. So I'm just sort of setting up an example where I'm trying to discriminate between the gamma family and the normal family, for example, to see which one's better. So even though I know I generated these from a gamma distribution, pretend like someone just handed me these data. If I was just handed this histogram, it might be difficult for me to look at this histogram and know, is that a normal or a gamma? So I might then go to my QQ plot. And so this is a QQ plot for both the hypothetical gamma and the hypothetical normal. So I've got the data we know was generated from gamma, but again, pretend we don't know that. It's just data that was handed to us. And so we've got it evaluated against gamma and normal, and they both kind of fit the line just as well. I mean, there are some red points that are above, there are some green points that are below, there's some red points that are above, green points that are below. The QQ plot looks pretty good to me for both of those. So then I go to the PP plot. And so the PP plot here, this red line, that's for the hypothetical gamma. and this green line is for the hypothetical normal. And as you can see here, the red dots are right on this diagonal. And so in this case, in PP plots, the actual X and Y axis are both always going to be from 0 to 1 because you're plotting probabilities against each other. So you really are looking for them matching this 45-degree diagonal. And those red lines are much better than the green line. So that's an example of what I mean, where you start with a QQ plot and you know, yeah, a gamma with the right parameters or a normal with the right parameters, both of them get me close. But then the PP plot helps you further discriminate. So I would probably include both the QQ plot and the PP plot in, like, if I was preparing this and, you know, in a technical document somewhere in the appendix somewhere to help justify why I did this input model, I would include both of these plots to provide evidence that I'm just not making the stuff up. Really, this is driven by data, and this is a much better fit. The gamma distribution is a much better fit to these data than the normal. Okay, so questions about that? Does that make sense, the process there? And again, the fat pencil idea is that, you know, you're looking for, if you lay a fat pencil on this, if you kind of make the pencil thinner and thinner and thinner, you like distributions that you're covering up the diagonal as well as the data points as much as possible. And so the red one could easily be covered up by a fat pencil. The green one, it's a little harder. Okay. All right, so you know, just general tips. Look for lines in QQ plots. A large region of linear relationship is a good candidate family, but systematic deviations tell you choose a different family. Use those deviations to help you choose a different family. If there are no deviations, then try a PP plot and discriminate among the ones that don't have huge deviations in the QQ plot. And then generally, don't start with a PP plot. If you start with a PP plot, they're not always informative. If you have distributions that are very different in the tails, then often the PP plots, because they're really focused on the bulk of, you know, where most of the mass of the distribution is, then they don't do a great job helping you evaluate the tails. So you can end up trying to kind of evaluate mostly the middle of it and then have tails that are way off. And you just don't get that in the PP plot. So generally, it's better to sort of pin down the tails first with the QQ plot and then pin the rest of the distribution down with the PP plot. Okay. So that's our PPQQ overview. Questions? I feel okay about that. It would be excellent to see one of these or both of these plots in an input modeling report, certainly in a final report, to help you justify, you know, your choices. All right, so then we can move on then to today, where we're saying, well, okay, we've now chose a good family of distribution. So let's figure out how to choose the member of the family that is the best fit to our data, and then evaluate how good that fit is. And so that requires us to go back to a little bit of stats before we have our big stats review, I think in lecture I, maybe, or H. And so the, you know, level of significance. So the meaning of level of significance. So if I were to ask you, you know, how do hypothesis tests behave when this level of significance you're requested for is 0? What does that mean? Like, so you're used to us saying, assume that, you know, do a chi-squared test and the level of significance is 0.05, or do a t-test and it's 0.05. And maybe we'll get a little, you know, coy and we'll say, oh, well, actually the level of significance is 0.1. And so then it shows you can use the tables right. Well, what, what does it really mean to lower the level of significance down to 0? How do we interpret that? Yeah. Well, 100% certain is an interesting. I like the idea of the no errors. So, do you remember what type of error that this alpha value, this level of significance, represents? Okay, there are two types of error: type 1 and type 2. Um, and so Does anybody have a description or is willing to brave enough to sort of hazard a description of either what type of error this one's associated with or what the errors mean? Do you want Okay, yeah, so the statement there is maybe type one is rejecting the null hypothesis when you shouldn't reject the null hypothesis. I think that's what you're saying there. So yeah, so that's basically what type one error is it's saying that we have a null, we have an expected, we have a hypothetical distribution. It might be uniform or whatever, and we have data. And we want to evaluate, did these data come from that distribution? And sometimes the data are there are data that did come from that distribution, but it just is kind of an anomalous case. So even though it did come from the distribution, it's so far away from what the standard way that data would be generated from that distribution that we falsely reject it. And so what a type one error, what the alpha value is it's supposed to be an upper bound on that. It's supposed to say if you have an alpha value of 0.05, then out of 100 times you do that test, if you only reject a null falsely 5% of the time. In other words, that if you get extreme data that it actually was from the distribution, you only falsely say that that extreme data is not from the distribution 5% of the time. You only have a 5% chance that that's going to happen. So what does it mean then to design a test that has an alpha of 0? It's a very easy to build a test that has an alpha of 0 so that you that basically means you have no type 1 error. That basically means that if that there will never be a chance that data are generated from the distribution and you falsely reject it. How do you guarantee that you will never falsely reject data? It's a very, very simple way to build a test. It's not a very useful test, though. So how do you guarantee that you never ever? So I give you data, and I say, hey, here is 100 data points. Test to see if they're uniformly distributed, and I want you to have a type 1 error of 0. So what do you do? What do you say back to me? And you thought, yeah. That's right. You never reject. Exactly. So if you just hand me data and you just say it's uniform or it's I fail to reject, you just say fail to reject. You just do not ever reject. You have an alpha of 0. Done. So it's a perfect test in terms of a type 1 error, but you have a lot of type 2 error. So now although you never falsely reject, you now have a bunch of cases where data were not generated from that distribution and you failed to reject them. So that's type 2 error. So there is a trade-off that we will talk about next week, I think, about from type 1 error to type 2 error. So with that in mind, what if I said, I thought I wanted a type 1 error of 0, but after hearing that story about, that's a useless test, I'm going to go the other way. Here's a bunch of data. I want, because I'm so worried of type 2 error, I'm okay with the threshold on my type 1 error being 100%. I'm going to set my alpha equal to 1. So how do you guarantee that you have an alpha equal to 1? If having an alpha equal to 0 means you just never ever reject, you don't even do any math, how do you guarantee that you have an alpha of 1? You reject everything. You just say, I don't like that data. I don't care what the data is. That data, reject, 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 reject. And 100% of the time you have data from the null, you will reject it falsely. So these extreme cases, we'll never actually have those, but that's what happens. As you start squeezing alpha closer to 0, or squeezing alpha closer to 1, then that's what you're doing. Squeezing alpha closer to 0 just means that you're going to have thresholds that you are unlikely to ever reach. So that chi-squared threshold, as you squeeze the alpha closer to 0, that threshold for your chi-square differences is going to grow to infinity. As you squeeze alpha closer to 1, that chi-squared threshold is going to go close to 0, to the point where nothing can meet it, and you reject everything. So that's the intuition we should get out of this. And so that's what I'm trying to say here, is that the chi-square test, t-tests the same way, is that the critical values do the opposite thing as the alpha values do. So a small alpha is a larger critical value. And those critical values, those are sort of related to how much difference you'll tolerate. So if you make your alpha small, then you tolerate a huge difference from what you would expect if in the hypothetical case was true. If you make your alpha large, then you don't tolerate any difference, and so on. So that's what we're trying to say here. It gets small and gets large. So there are questions about that, what I mean by that. I want us to start building up this intuition about critical values and alphas and how they relate. Okay. So with that in mind, then we can start thinking about p-values and what is a p-value and what is the meaning of it? How do we make sense of p-values? Because this really is important for goodness of fit, is that one of the metrics that comes out of our goodness of fit is this p-value. And so when, a p-value is this sort of case where you're saying, based on the data, if I assume that the hypothesis is true, that these did come from the hypothetical distribution, the null, but in this case, I want us to avoid using the null too much here, because in goodness of fit, the null is the hypothetical distribution. It's like, so don't think of it as a throwaway, as like the complement to what you're actually trying to show. The null is the thing you're evaluating. So we're trying to say we would like to see if these data came from a normal distribution. Well, then the normal is the null. And so what we're saying here is, assuming the null, the hypothetical distribution, is correct, what is the probability that the data that we see, or worse, would occur given that that's true? So given that the height distribution in the human society is a bell curve, then what's the probability that someone could be 6 feet or higher? And so eventually you're going to get to a point where it's like, oh, it's very unlikely to have an 8-foot tall human. So if someone were to report to me a height of 8 foot tall, then I'd say that can't be a human. That must be an elephant or something like that. And so I would reject the hypothesis of a human, height distribution. So this p-value is this, it's this probability that I would have that value or more extreme relative to this hypothetical distribution. That's how we interpret this p-value. So with that in mind, we can think about, there are scenarios that would generate very low and very high p-values that are maybe surprising. So a low p-value might actually be because you have a lot of data. It's not because it's a poor fit. It's just that, like you've said, I've taken 1,000 samples of this distribution. So I have a lot of data here. I've taken 1 million samples of this distribution. So then they're sort of saying that, the thing is, those samples are probably not going to be a perfect fit to that distribution. But the more and more samples that you take, the more sensitive your test is going to be at detecting that difference. So for 1 million samples, you might have something that it's a normal distribution plus a tiny little bit of noise. Well, that tiny little bit of noise, if you only took 10 samples, that tiny little bit of noise would just get lost in it's only 10 samples. I don't get a lot of info. But if you take 1 million samples, that tiny little bit of noise is going to show up. And whatever test you're using, chi-square test, KS test, is going to detect it and just reject it. And so in that case, it's really less about, it's when you see a super, super low p-value, like a p-value of 0.00001, that you then have to ask, wait a second, how much data were there? If there was a lot of data there, then you should ask, how different? Is there a measure that of this difference? What is the effect of the data? Like, what is the estimated effect, the estimated difference between the data and the hypothetical distribution? And then you can evaluate, is that little difference that was detected meaningful to me? So it's not enough for your p-value to be less than alpha for you to throw away a perfectly good distribution. You then need to then further estimate how bad it really is the fit. And that's why when we are going to get into this, when we get into goodness of fit, there are these other metrics like R squared that are going to be really important to us, because we're going to find that if you have a lot of data, Arena or whatever automated statistical tool you use to do the fits will probably have p-values that are all less than 0.05. And you can't just throw up your hands and say, well, I guess that's nothing. Or I guess, there's no model that fits it. If you look at the histogram, you're like, actually, this really looks like it fits the histogram really well, then we need another measure of fit. So a p-value is by itself not a good measure of fit. A low p-value does not mean you should reject an input model. It might mean that, but you really have to evaluate how much data you had and how bad the mismatch is. Large amounts of data, you're going to detect every mismatch, and the p-value is almost useless for goodness of fit. On the flip side of that, what if I get a really high p-value? I get a p-value of 1 or 0.6 or whatever. You might say that's an indication that that's a good fit. There is a high probability that if the null hypothesis was true, that I would get these data. But it might just mean you have very few data samples. If I don't have a coin on me, but if I did, and I flipped a coin and it came up heads, there's all sorts of hypothetical distributions on the fairness of that coin. It could always come up heads. It could come up heads 50% of the time. It could come up heads 75% of the time. Just knowing that it came up heads once in my hand does not allow me to discriminate. And if I put in any one of those hypothetical distributions, fair coin, totally unfair heads, half or 75% heads, 25% tails, and so on and so forth, all of those p-values are going to be greater than my significance level. And a fair coin that comes up heads is probably going to have a higher p or a lower p-value than an unfair coin that always comes up heads. So if I just ranked things by p-values, if I have very little data, then I might end up picking an input model that is sort of overfit to the few number of samples that I have. And because I only saw heads once, then my input model will only generate heads because that was the best p-value. So low amounts of data, regardless of fit, will generate high p-values. High amounts of data, regardless of fit, will generate low p-values. So you can't operate on p-values alone, is what we're saying here. And that's kind of walking through an example here. So this is my coin example. Let's say I flipped a coin twice. It comes up heads twice in a row. Well, a fair coin, if I do a binomial test, then I could say, well, the binomial test p-value is 0.5 for these data. So that's basically saying, what's the probability that I would get if I were to flip the coin twice and it was a fair coin, what's the probability that it would come up with this two heads? Or worse, I guess, but there's no worse in this sort of case here. And it happens to be 0.5. But if I instead choose an alternative hypothesis where it only comes up heads, then the p-value is a 1. So if I just rank things, it was a fair coin. I'm telling you ahead of time, I flipped it and it just happened to come up heads twice. That happens. If you flip coins, it's very unlikely for it to be heads then tails and heads then tails because it's like a random number generator. Every flip is independent of the previous flip. So if it comes up heads, it's very likely that it's going to come up heads again. So if I get 2 heads in a row, that's a reasonable outcome for a fair coin. But by p-value, it's slightly more likely that that would happen if it was a pure heads coin, a coin that only comes up heads. So I can't just rank by p-value. So I have to interpret this as I have low power. I have not that many samples. I probably should get more samples. And so if I flip it 200 times and it comes up heads 90 times and I test the hypothesis, well, now the fair coin has a p-value that is greater than 0.05. Don't reject. But then that fair coin, if I did it 2,000 times and it came up heads 900 times, now I have extremely low p-value. So in the previous case, a false hypothesis had a higher p-value because I had low data. In this case, the true hypothesis has a p-value that's less than my significance level because I have so much data. So when you're doing goodness of fit, you can't depend entirely on p-value, but you have to pay attention to it. But it's not the only information you should use. So are there questions about these two examples? Do you see how decreasing data increases p-values and increasing data decreases p-values, regardless of how close or not your data are to the null? This is a big reason why big data people aren't into hypothesis testing. Because if they tried to test a lot of different hypotheses in the rigorous kind of experimental ways that you would if you were setting up an experiment in the real world, the amount of data that they use would just reject everything because it would detect every tiny little difference. And that's what we're basically saying here is that, with more and more data, you detect small differences, but sometimes you don't care about small differences. But the test doesn't care, it doesn't know how big of a difference. And so we have to deal with that. So what we're going to be talking about as you get into homework H is how to adjust our hypothesis tests to account for the size of the effect we do care about so that we end up not getting into this trap. Okay. So always be careful about using p-values. Just remember this, large p-values are only meaningful if there's a lot of data, and low p-values are only meaningful if there's sort of, not too much data. So modern approaches are to infer effect sizes instead. So the modern approach is to use like linear modeling tools like regression analysis. And if you have a lot of data, it's better to sort of fit a multivariate regression model to it. And then you can ask, what is the relative effect of one thing over another and compare those effects to each other? And you might find that some things I could detect an effect, but their effect is much smaller than other things I could detect an effect. So I should focus on the things that generate the bigger effects than the littler effects. And so that's outside of the scope of this class. But I'm putting it there to show that that doesn't mean we should just throw hypothesis testing out the window. There is a next step. When you have large amounts of data, that's why the econometrics people, the economists or whatever, they have a huge amount of data. So when you take a stats class from an econ person, they don't even teach you t-tests and things like that until like the week at the end of class, because to them, they're kind of these sort of cute add-ons. To them, it's all about regression analysis. So it just kind of depends on your discipline what you focus more on. But the point is, once you get up into these big data regimes, there are approaches you can use. But for this class, we're in the kind of smaller data regime where things like t-tests and so on, ANOVAs, whatever, still make a lot of sense for us to use. I've sort of harked on this more than I needed to anyway, but now that we're going into the World Series, I guess I might mention this as well. If you do that same analysis that I just did with the coin flipping, but you think about it in terms of 7-game series, then it starts making you wonder like why it's ever worth spending that much time watching that much baseball, for example. Because it turns out that if you use, ideally, the null hypothesis is that the two teams are equally ranked, and you're trying to put them in a tournament to see which one's better. So you're trying to detect the deviation from the null. Are they, is this one better than that one? And you can ask, what's the minimum number of games that I need for me to make that determination? And again, I don't want to spend too much more time on this, but basically what the punchline ends up being, and you can walk through this on your own, but the punchline is here that the only win I think you get to 8 wins can you actually say that one team is better than another. But in the World Series, you won't ever get to that. And if you did, it would be really, really boring. If you get 4 wins right in a row, that's basically 4 heads. So you can take a fair coin and flip it, and it could come up heads 4 times in a row in your palm. That happens. It doesn't happen that often, but it does happen. If you stop the series there and say, heads, this coin is definitely unfair, heads is definitely the one that dominates, then you will be wrong more than we allow you to be wrong in most statistical settings. So stopping after 4 games and 4 wins, that definitely doesn't tell you who's better. So you really do have to go once I go to 7 games and where you've got 4 wins, I'm still not really even close there. So I really do need to get all the way up to like 7 games and 7 wins, I think, like that. So again, I don't want to. Usually I walk through this, but I feel like I've already spent too much time on this. But the point there is that the point is a lot of times we watch sports because we're looking for ways to form communities, and in the end, it doesn't matter what we're watching because it has a random outcome, and that's really what we're sort of saying here. So if your team doesn't win the World Series, you shouldn't be upset about it because it's just random. It's basically a coin flip anyway. But at least you got to spend a whole heck of a lot of time with a bunch of friends. That's really the point of sports. If they really cared about who won, they would play more baseball, but nobody wants to watch that much baseball. It's really kind of enough after 7 games. So that's why they stop it there. It's a marketing thing. So the essential things here: alpha, type 1 error rate, maximum acceptable probability of rejecting a true null; beta, type 2 error rate, maximum probability of not rejecting a false null. We are going to start using the term statistical power. That is 1 minus type 2 error. So you can think of it as the minimum acceptable probability of rejecting a false null. That will make more sense as we go on in these next couple of lectures. And then the necessary number of samples. This is something you'll get to play with in homework H on that second part. And so this is basically, if I give you a desired type 1 error rate, and if I give you a statistical power, a desired statistical power, which is basically a type 2 error rate, and then I also give you a minimum detectable difference from null. So I'm sort of saying, I really want to make sure that my data are no more than 5 inches from the average height. If it's less than 5 inches, I don't really care about that. That's basically the same distribution. But if the mean for my hypothetical distribution is more than 5 inches from the mean in the real data, then I really need to be able to detect that. If you give me all of those things, the type 1 you want, the type 2 you want, and that minimum detectable difference, I can then say, you better sample at least 15 individuals, or you won't be able to meet those criteria. That's what we refer to as a power analysis. Likewise, if somebody comes to me and says, I sampled 10 individuals, then you can come back to them and say, well, that's not enough to meet these things. So based on the 10 individuals here, your type 2 error might be inflated, and here's the value it is. So power analysis either goes from samples to error rates, or from error rates to required number of samples to meet those error rates, given this minimum detectable difference. And that's something we're going to practice with on the second part of homework H, which we'll go over in lecture H. And then there are these other alternatives outside the scope of this course where you get rid of frequentist statistics entirely. So I just am mentioning the term Bayesian or Bayesian approaches. Again, we're not going to talk about that. You don't need to know anything about that to test, but just know that there are completely different statistical frameworks that are specifically designed for this idea of accepting hypotheses. So this hypothesis testing is really about rejecting hypotheses, and statistical power is about having enough sensitivity to reject enough of the hypotheses. And then an alternative that was dreamed up is to say, well, if you really care about fitting models, then really let's rebuild a statistical framework based on kind of accepting things, not rejecting things. And that's really what Bayesian approaches are all about. Okay, so any questions about those? Basically what I want to take, what you would, right now, I want you to have a deeper understanding of alpha and P. That's really the big thing for this goodness of fit stuff that I want you to know. So any questions about that? The alpha and P, how P can go up and down based on samples? Okay. All right, so we're gonna then apply that. So we've got our data, we've come up with a family. We now need to parameterize the family and evaluate those parameters. So our next step here is to to sort of think about the physical meaning of these parameters. So if we've chosen a distribution where we kind of know, like if we've chosen a binomial distribution, there's n is the number of trials that each have a success probability of p. Well, sometimes knowing what those parameters mean help us move toward how to fit those parameters. So you know that certain parameters, there's no way they can be less than this or more than this, or maybe they're automatically fit from, if something looks like a binomial distribution, then I need to ask, if it is a binomial distribution, I should know this n ahead of time just based on the description of the problem. Or I need to know ranges. And so I might, know, is it possible for these parameters to be positive, negative, and so on? So I need to sort of think about, are there physical constraints on these parameters just based on the problem itself? And I need to make sure I respect those. So that's one thing of that. And then there are types of parameters that we give these fancy names. So there is sort of a generalized idea of a mean that we call a location parameter. So when people talk about families of distributions, if you were to look up on Wikipedia for the Weibull distribution or whatever, you might see them refer to a location parameter or a scale parameter. And so the location parameter is basically a parameter that if you change it, that family member will just move left and right. It won't change its shape. A scale parameter is a parameter that allows so it's shifted left and right and it stays within the family. It just moves left and right, but it's still a family member. It's still a type of that distribution. Likewise, a scale parameter is a parameter that if you change it, then the result you get might change its spread, but the thing that you get out is still a member of that family. So those are special terms we get. Any other parameters that don't fit that mold are just known as shape parameters. And so there's examples here where, like in the normal distribution, the mean is a location, the standard deviation is a scale, and the exponential distribution, it has a scale parameter, but we often use 1 over it. It's just convenient. For the thing that would normally be considered a scale parameter, we take its reciprocal, and the reciprocal of a scale is a so-called rate. So these are the terms that when you talk about distributions, if you look them up, they're going to name the parameter types, and very often they'll use location, scale, and rate. And you can just think of those as sort of generalized versions of mean, standard deviation, and 1 over standard deviation. They're sort of like, to things that are weirder than a normal and an exponential, they still function like those things, but they aren't technically mean or standard deviation, but they have these properties. So I'm not too worried that you know that, but I just wanted you to be exposed to those terms, as if you look up distributions, you'll see parameters being called these things: location, scale, and rate. All right, so then before we get into distributions, we have to talk about sample mean and sample variance. And so these are your summary statistics. These are statistics you take on the data before you even assert that they have a distribution. And you use summary statistics to often calculate the best fitting parameters for your distributions. So if you have a bunch of data, arithmetic mean, sample mean, sample variance, notice in the variance equation, if you have to calculate variance yourself, notice that there's this n-1 down here. You have to, when you calculate variance, the formula for variance that you should have for back when we were talking about probability had what you might think to be an n here. But when you don't know the real mean of the data, when you first have to calculate mean and then plug it into the variance formula, you get rid of a degree of freedom. Basically, one of your data points disappears because once you know your data, once you know n-1 data and the mean, you know that other data point because it's fixed by this equation here. So in order for you to calculate variance, you have to divide by n-1. So that's often missed. But so if you ever have to calculate variance, if you're calculating the mean first to plug into here, because you don't know the real mean, you have to divide by n-1. So it seems minor, but it's a really big thing, or else you'll get a biased estimate of your variance. For discrete random variables, we also add frequencies to those variables. So you have outcomes, but then you also have numbers, how frequent each outcome is. So you had 1,000 data points, but there were only 3 outcomes. And so there was like 300 outcomes, 600 outcomes, and 100 outcomes across those 3 specific outcomes. So there were, so it's the count of each one. And when we specify things that way, then we use this formula, which is like the outcome times how often it occurred, add all those things up together, divide by the total. And then likewise, we've got the n-1. If you had to calculate this x bar to go into this formula, then that should be an n-1, not an n. If somehow by some magic, someone's given you the mean and it's not related to the data, it's just known that's the mean, then you can divide by n here. But otherwise, if you're calculating variance, after you calculated an estimate of the mean, you have to use n-1. Okay. And then likewise, if it is observed frequencies, if a histogram, even if it's continuous data, if somebody's thrown away the data and just given you the histogram, you treat it like discrete data. And you just treat the middle of the bins as discrete outcomes and then same formulas. All right. Any questions about that? This is the summary stats and why we use n-1. Okay. So example is somebody gives you this table, which is outcomes that were drawn from a Poisson random variable. So you only see these outcomes in the data, and each one of these counts has its own frequency. It's like a count of the counts. And so you calculate your mean by by basically multiplying across these columns and then adding the result together. And then you can get your X bar after doing sort of this math here, because you take that X bar, you plug it into the variance equation, and you get this outcome here. And then note that in the Poisson has this funny property that the mean is equal to the variance in probability distribution. So in the ideal case, the mean is equal to the variance. But when you actually calculate the estimate of the mean and the estimate of the variance, they're very far off. So don't expect ideal relationships to work, because as we're going to talk about as we get further down, by the end of this semester, I don't want you ever taking point estimates unless you absolutely have to. On your final reports, when you generate data from ARENA, you should have confidence intervals everywhere, because there's no such thing as a point estimate. A point estimate is it basically is something that you have 0 confidence in. So it's like a confidence interval. It's like a 0% confidence interval. So, and that's basically what these are. So this is an estimate of the mean, but the real mean of this Poisson distribution is within an interval that's centered around this point. The real variance of this Poisson distribution is in an interval that is centered around this point. Those 2 intervals probably overlap, and the real mean and variance is probably in the overlap. But we have no idea what it actually is, so we go with the point estimates here. But because there are these 2 intervals and they were estimated in different ways, they don't necessarily agree. So it is the case that for Poisson distribution, mean is equal to variance, but it won't necessarily be that case for the estimate. So if you wanted to plug this into a Poisson, you're just gonna have to pick one. Do you want to be correct in the variance, or do you want to be closer to the variance or closer to the mean? You only have one parameter to put into a Poisson, so you just kind of have to pick one of these 2. But once we start getting into these confidence intervals, it'll be and other ways to estimate these things, it'll become clearer on other options. But so there are questions on what I mean here, that these point estimates, you should not take them as the real values. They are in the ballpark of the real values, and really there should be a confidence interval around them, and the real value is 95% of the time in that confidence interval. Okay. So summary statistics are great without a particular distribution, but we need to generate point estimates of the distributional parameters themselves. So one of the ways we're going to do that is with so-called maximum likelihood estimation. So this should hopefully be a review from things I think you've done in either 380 or 385. But the basic idea here is that we can, if we have a density function like f here, normally we view the variables, X is the variables, they're the things that are free, and the parameters are set ahead of time. Well, we can go the other way around. We say, well, we took the data, we don't know what the parameters are. So we kind of treat the data like parameters. We're going to put the data in as if they're parameters, and that will leave the parameters as being the free variables. And then we're going to use calculus to maximize them. That's what maximum likelihood estimation is. So an example of that, let's say that we have data that we are pretty confident is exponentially distributed, but we don't know what rate to use, what parameter to use. So what we're going to do is we say, well, if we have a bunch of data, in samples, if we assume they were sampled independently from each other, then by probability law, the joint distribution of those in samples is the product of the individual, the marginal distribution of each one of those. And so we can basically say, rather than having to deal with an n-dimensional exponential surface, it's just the product of each one of these individual exponentials multiplied together. Well, that's great because for an exponential, I know what this form is. So I can just plug that in and get a functional form. That's what that is right there. I just plug, and then these data points that are up here, normally those would be the variables, but I took those data, I'm going to treat them like parameters, and then all that's left over is this lambda. So now I can just take the partial derivative of that expression with respect to lambda. There's just that one variable. So I get that's my partial derivative there. If I set this thing equal to 0, as I would if I was optimizing this, maximizing this, then basically this thing divides out, and this is what ends up getting set equal to 0. And now I can solve for the optimal lambda, the optimal rate. And what does it end up being? It turns out that it's exactly equal to the reciprocal of the sample mean. That makes a lot of sense, but we can't assume that ahead of time. Maximum likelihood estimation gives, there are some cases that I'll show you where you're going to get formulas that involve the summary statistics, but they aren't directly equal to them. Here, this is basically saying that the best thing to do is to set the mean of your hypothetical exponential equal to the mean of your real data. That's what this is saying here. But we got it rigorously by solving for the maximum log. We basically maximize the probability density given that we had these data points, and we maximized it over the space of all parameters. All right, so any questions about that? This idea of maximum likelihood estimation? And that's a simple case for an exponential. You could do this for Poisson, for normal, for log normal, for a bunch. If you look up each one of these distributions, then it would give you suggested estimators based on the maximum likelihood process. The exact same process I just did, you could redo, and you get these estimators. So they happen to work out to things that make a lot of sense. But again, there's no reason to believe that they're always going to be that way. All right. I think we're going to stop there. So let me get an iClicker up. And the question I have for you, there it goes, is what day this week are your final project report team names due? When are your team names due? When should you all have attempted to put together a team and have them for me this week? And that's all I've got for you. So we'll see you next week. And those of you who can't find a team, I probably will be bugging you over the weekend. Mhm.